Hi everyone, my name is Michael Pendazis and this is Math 231 Linear Algebra online lesson number 7, and we are going to be covering sections 4.3 to 4.7. So we're going to finish 4.3 and try to go all the way to 4.7. So let's get started. Okay, so in 4.3, continuing 4.3, Theorem 4.3.3, we have let S be this set, V1, V2 to VR. Okay, and let this be a set of vectors in Rn. If little r is greater than little n, then capital S is linearly independent. Is linearly dependent. Sorry. Okay, so this is theorem 4.3.3. You have a set S of R vectors in Rn. If little r is greater than little n, then capital S is linearly dependent. Okay, so that's that theorem. Here's a definition. If f sub 1 is equal to f of x, f sub 2 is equal to f sub 2 of x, dot dot dot, f sub n is equal to f sub n of x. Our functions n minus 1 times differentiable. Okay, n minus 1 times differentiable means that it has a derivative, has a first derivative, second derivative, third derivative, up to and including the n minus first derivative. On the real line, which you can say it's that interval from negative infinity to infinity, that means the domain of each of these functions is the entire real line. Then the determinant w of x, which is equal to the determinant of this matrix, okay, so if the determinant wx, was determined of that matrix, is called the Wronskian, is the Wronskian of the functions f1 up to including f sub n. And so this is the definition of the Wronskian of the functions f1 to fn. It's the derivative of that matrix, where the first column, first vertical column, columns are vertical, rows are horizontal. First column, f1 of x, f1 prime of x, so then stopping at n minus first derivative of f1. Second column, f2, f2 prime, then up to including the last one, the n minus first derivative of f2. And then you keep going, the next column would be f3 and its derivatives, the next column after that would be f4 and its derivatives, and the last one would be f sub n and its derivatives up until the last one, which is the n minus first derivative of f sub n. Okay, and so the determinant of this entire thing is called the Wronskian of f1 to fn. Okay, that's the name of it, the Wronskian of f1 to fn. And so that's the definition. Okay, let's keep going. So we have a theorem at the top there, and then we have a definition after that. Okay, I'm going to try to separate things into boxes, and so I want you to look at each box separately. Okay, Theorem 4.3.4. If the functions f1, f2, up to including f sub n, have n minus 1 continuous derivatives. On the interval, negative infinity to infinity on a real line. And if the Wronskian of these functions is not identically 0, on the real line, use that for notation for, then these functions form a linearly independent set of vectors in Cn minus 1 on R. Okay, so theorem 4.3.4 is in this box. And if the functions f1 to fn have n minus 1 continuous derivatives on the real line, and if the Wronskian of these functions is not identically 0 on the real line, that means it's not always 0. There's some input into the Wronskian that would make it non-zero. So it's not identically 0, right? On the real line, that means it's not always 0. Then these functions form a linearly independent set of vectors in Cn minus 1 on R. And so this is the set of n minus 1 times n minus 1 continuous functions that have n minus 1 times n minus 1 continuous derivatives on the real line. Okay, that means these are functions that are continuous, has a first derivative that's continuous, second derivative that's continuous, third derivative that's continuous, up to including the n minus first derivative that's continuous. Okay, so if n was 7, n minus 1 would be 6. And so Cn minus 1R, that would be the functions, if n was 7, that would have continuous derivatives from 0 to 6. And so the last one would be the sixth derivative would be continuous of the function. Okay, that was 7. So the conclusion is that those functions form a linearly independent set in that vector space. Okay? And so in example 8, we're going to see an application of this theorem. Okay? So in example 8, you want to use the Wronskian to show f sub 1 is equal to 1, f sub 2 is equal to e to the x, and f sub 3 is equal to e to the 2x are linearly independent vectors in C infinity of negative infinity, comma infinity. Okay, so we're going to use the Wronskian to show that those three functions are linearly independent vectors in C infinity. Okay, and so the solution is that the Wronskian is w of x, which equals the derivative of f sub 1 of x, f sub 2 of x, f sub 3 of x, f sub 1 prime of x, f sub 2 prime of x, f sub 3 prime of x, f sub 1 double prime of x, f sub 2 double prime of x, f sub 3 double prime of x, right? So it's the derivative of that function for 3 functions. The derivative of that matrix for 3 functions. So that's equal to the derivative of 1 e to the x, e to the 2x. The respective derivatives are 0 e to the x, 2 e to the 2x, and then 0 e to the x, 4 e to the 2x. Okay, and you find the determinant of this. You can use the cofactor expansion along the first column. And so when you do that, you get the determinant of e to the x 2e to 2x, e to the x, 4e to 2x. And a term of that is equal to 4e to the 3x minus 2e to the 3x. And that's equal to 2e to the 3x. And that does not equal 0 when x is 1. Right, so when x is 1, the Wronskian is equal to 2e to the 3x, and when x is 1, you would get 2e cubed, which is non-zero. And so Theorem 4.3.4 says if the Wronskian of these functions is not identically 0, meaning there's some input into the Wronskian that makes it non-zero, then these functions form a linearly independent set of vectors. Then the conclusion is that these functions form a linearly independent set of vectors there. And so we want to show that they are linearly independent. Okay? And so we did that. By showing the Wronskian is not identically 0, then we reached the conclusion by this theorem that they are linearly independent. Okay? Again, saying it's not identically 0 means that there's some input into the Wronskian that would make it non-zero. It doesn't have to be non-zero everywhere. There just has to be at least one input that makes it non-zero. Okay? Okay, and that's example 8. And it uses the theorem. So definition. A vector space V is finite dimensional. Here, this capital V is a vector space. Is finite dimensional if there is a finite set of vectors in capital V that spans V. It is infinite dimensional if no such set exists. If no such set exists. A set that spans. Okay, so if capital V is capital V as a vector space is finite dimensional if there is a finite set of vectors in V that spans V. It is infinite dimensional if no such finite set exists. The set I considered was finite, and so such a set is a finite one, right? Okay? So that's the definition of a finite dimensional and infinite dimensional vector space. Okay? Remember the span of a vector, a set spans V if every vector in that vector space can be written as a linear combination of the vectors in set S. Right? So note the span of S equals V if this is a reminder, if every vector little v in vector space capital V is a linear combination, can be expressed or is a linear combination of the vectors in set S. Right? So the span of a set of vectors S in V is equal to capital V if every vector little v in capital V is a linear combination of the vectors in set capital S. Okay, and an example of that would be the span of the set 1, 0, 0, 1 is equal to R2. Every vector in R2 is a linear combination of these two vectors. Okay? Okay, and so that is the end of 4.3. Okay, so we're done with 4.3 at that point. 4.4 coordinates and bases. Definition 1. If S is equal to the set V1 to Vn is a set of vectors in a finite dimensional vector space. Capital V. Then capital S is a basis, is called a basis for capital V if the following two hold. A, capital S spans V, and B, capital S is linearly independent. This is really important. And so I'm going to star this after I box it. So it's very important that you independent. Okay, so this is definition 1 in 4.4, and I'm going to star it because this is extremely important. Okay, so definition 1, if capital S is that set, is a set of vectors in a finite dimensional vector space capital V, then capital S is a basis for V if S spans V, and B, S spans V in A, and B, capital S is linearly independent. Okay? So you need to know what it means for a set to span a vector space, and you need to know what it means for a set to be linearly independent. And so if you know those things, and you have to know what a finite dimensional vector space is. Okay? So I'm going to squiggly underline the things you need to study before this in order for this to make sense. You need to study what a finite dimensional vector space is. You need to study what a set spanning a vector space is, and you need to study what a set being linearly independent means. Those three things I squiggly underlined is supposed to be understood before this definition, right? And so in order for this definition to make sense, you have to know those three things before this definition, okay? So if a set S is a set of vectors in a finite dimensional vector space V, then S is a basis for V if S spans V and S is linearly independent, okay? The logic of it is just, right? It's just, these are the assumptions. You have a set S here. V is a finite dimensional vector space. And it says that with that given, if these two things happen, then capital S is a basis for V. All right. So the conclusion is our set. This set S is a basis for your vector space V. That's the conclusion. And the hypothesis, the things that have to be true hold are these two things. If these two things hold, then capital S is a basis for V. That's basically, with some given information, that's what this definition says. Okay. It's a definition of a basis for a vector space. Okay. So make sure to study those three things that I underlined, and then that'll make more sense. Okay. So a basis is sort of like the core axes of a vector space. So for instance, if you had the xy plane, right, you might think of the x-axis and the y-axis. If you thought of a basis, this is R2, right? R2 is all the vectors in 2 space there. If you thought of the vector E1, which is the vector 1, 0, and the vector E2, which is 0, 1, these two vectors form a basis for R2. Okay? So E1, E2, this set E1, E2 is a basis for R2. And E1, E2 are on the x and y axes respectively. And so you can think of these axes coming from a basis for the vector space R2. Okay? And then if you had R2 still, the same R2, right, where here's the x-axis and here's the y-axis, but instead I had a different basis. You could have more than one basis for the same vector space. let's say I took the vector 1, 1, and the vector -1, 1. Then the set of vectors 1, 1, -1, 1, that would also be a basis for the same vector space R2. But then I can think of the lines going through those two basis vectors, and I can think of one axis being x prime going through 1, 1, and the other axis being y prime going through the other vector -1, 1. And so while I had the original core axes x and y, and the basis vectors were along x and y, respectively, now instead of the core axes being x and y, I can think of two core axes x prime and y prime, where x prime goes through this vector and y prime goes through that vector. And the core axes don't have to be perpendicular to each other. I kept them perpendicular here, just like they were here. But you don't have to have perpendicular core axes. You could have a core axis. Here's the regular x and y. I could have an x prime that looks like this, and I could have a y prime that looks like that. And why we would want that to be core axes is not because they're perpendicular, but because I could get to any point in R2 by moving some length along x prime and then some length in the direction of y prime. Okay? And so a basis vector could be a vector along x prime, and another basis vector would be a vector along the core axis y prime. Okay? So your basis vectors are kind of where your core axes would come from when you're just looking, when you're thinking geometrically about a vector space. Okay? Okay. All right. Okay, so you saw there how there could be three different bases for the same vector space R2. There actually could be infinitely many different bases for that same vector space. Okay, so an example 1 of a basis. Let's say the standard unit vectors. E1 to En of R to the N. Okay, those vectors are linearly independent. Okay, they're linearly independent because if I took C1 E1 plus C2 E2 plus dot 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 plus Cn V En, and I set it equal to 0, saying that these n vectors are linearly independent would be equivalent to saying that the only solutions for the C's is the only solution for C's is when they're all 0. Okay? So saying that equation only has solutions when all the C's are zeros is equivalent to saying that E1 to En are linearly independent. Okay? And so since it's true that the only solution to that equation is when all the C's are 0, then since they're logically equivalent, they have the same truth value, it's true that E1 to En are linearly independent. So they're linearly independent, and they span, E1 to En spans Rn. If I take any vector V, which is V1, V2 to Vn, I could say that vector is a linear combination of those n vectors, because I could say V is equal to V1 E1 plus V2 E2 plus following the pattern plus dot 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 plus Vn En. And here I've expressed the vector V as a linear combination of E1 to En. So every vector in Rn is expressible as a linear combination of E1 to En. And so E1 to En spans Rn, that's also true. And so the set S of those n vectors, E1, E2 to En, is a basis for Rn. It's a basis because in the definition of a basis, we can say it's a basis because it's linearly independent and spans all of Rn. Okay, so that set S is a basis for Rn. Okay, and so that's our first example of a basis. Example 2. Okay, the set S, which is the set 1x, x squared, up to including x to the n, form a basis. For p sub n of polynomials of degree n. Of degree n or less. Since capital S spans p sub n and is linearly independent. Okay, so in example 2, that set S forms a basis. For p sub n of polynomials of degree n or less. So p sub n is a vector space of polynomials of degree n or less. Okay, that set spans p sub n and it's linearly independent. I'm going to switch to the blue marker. Okay, good. Okay, and so it spans p sub n because every polynomial in p sub n, if you took a polynomial a naught plus a1x plus a2x squared plus plus a sub n x to the n, that would equal to a naught times 1 plus a1 times x plus a sub 2 times x squared plus plus a sub n times x to the n. And so now I've expressed an arbitrarily polynomial in p sub n as a linear combination of the vectors 1, x, x squared up to including x to the n. And so this implies that capital S spans p sub n. Okay? Capital S spans p sub n. And that's linearly independent because the only solution to the equation, C1 times 1 plus C2 times x plus C3 times x squared plus plus, we'll do this, C naught, C1, C2 plus C sub n x. The only solution to that equation, the only values, the C values that would make that 0, is if every term is 0. This would have to be 0, and this, and all the ones in between that. And that could only happen, that's equivalent to saying all the C values are equal to 0. And so as that is the only solution, that means that whole thing, right, this whole thing here, saying the only solutions are when all the C's are 0, that implies that S is linearly independent. Okay, so S is linearly independent, S spans V, and so if you have a set that's linearly independent and spans a vector space, it's a basis for it, by the definition of basis. Okay? So example 3, we want to show V1 is equal to 1, 2, 1, V2 which is equal to 2, 9, 0, and V3 which is equal to 3, 3, 4, form basis for R3. Okay, and so here's a solution. So V1, those are vectors V1, V2, V3. We want to show they form a basis for R3. So we need to show the set S, which is the set V1, V2, V3, is linearly independent. And that the span of S is equal to R3. So if we could show that set is linearly independent and spans R3, then by the definition of a basis for R3, S is a basis for R3, okay? Those three vectors form a basis for R3. Okay. Saying a collection of vectors saying a bunch of vectors form a basis for a vector space means that the set of those vectors is a basis for that vector space. Okay, so we want to show it's linearly independent. So let's do that. So first for linear independence, what we're going to do is we're going to say C1 V1 plus C2 V2 plus C3 V3 is equal to 0. And then we're going to find all the values of C that satisfy that equation. If it has at least one assignment for all the C values that make this equation hold, then they're not linearly independent. The only solution can be when all the C's are 0. Okay? So this is C1 times 1, 2, 1 plus C2 times 2, 9, 0 plus C3 times 3, 3, 4 is equal to 0. Okay? And so then when you combine the terms, you get C1 plus 2C2 plus 3C3, 2C1 plus 9C2 plus 3C3, C1 plus 4C3 is equal to 0. Okay, and so this is only, and by 0 we mean the 0 vector, 0, 0, 0. Okay, and so we have to say that this is equal to 0, that that's equal to 0, and that this is equal to 0. Okay, in order for those 2, 3 tuples to be the same, their corresponding components all have to be the same. Okay, and so in order for this to hold, for an assignment of C values, we get this corresponding linear system. C1 plus 2C2 plus 3C3 is equal to 0. 2C1 plus 9C2 plus 3C3 is equal to 0. C1 plus 4C3 is equal to 0. Okay, so we get that linear system. And so we have to find all the solutions of that linear system, and then we're done. Okay. So I'm going to erase this part, and I'm going to continue this part of the solution by finding all the solutions to that linear system. And so this is the corresponding augmented matrix. 1, 2, 3. Okay. 2, 9, 3, 1, 0, 4. And then I'm going to get this to reduce to echelon form. So 1, 2, 3, 0, 0, 5, negative 3, 0. And then 0, negative 2, 1, 0. Then continue 1, 2, 3, and then 0, 1, negative 3/5, 0, and then 0, 0, and negative 1/5, 0. And then the last step here, 1, 2, 3, 0, 0, multiply that by negative 5, and then 3/5 times this added to that. You get that. And then if you add negative 2 times this row of that, negative 3 times that row of that, you get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? So now I found that the only solution is then when C1 equals C2 equals C3 equals 0. And so the only solution to our original equation is that all the C's are 0. And that means that we have linearly independence. So linearly independent it is. Okay? And the next part we're going to show that it spans R3. I can do this a little faster than the other way. So what we need to show is that C1 V1 plus C2 V2 plus C3 V3 is equal to V for any V in R3, right? Well, multiplying this out again, you get 1, 2, 1. Equals the vector V1, comma V2, comma V3. Okay, and so then so then you want to show that that's equal to that. And for some, so you want to find, for an arbitrary choice of v1, v2, v3, are there values of c that make that equation true? Okay? And so this linear system, you could, if you took this, you would get c1 plus 2c2 plus 3c3, comma 2c1 plus 9c2 plus 3c3, comma c1 plus 4c3 is equal to 0. Okay, so then, okay, so you have that's equal to 0. Now, okay, so again, we have our, oh, not 0. Sorry, v1, v2, v3. And so, right, so our corresponding linear system now is c1 plus 2c2 plus 3c3, 2c1 plus 9c2 plus 3c3, and c1 plus 4c3. This is equal to v1. This is equal to v2. That's equal to v3. That's our linear system. Okay. Now, we have a theorem that says that if ax equals b is consistent for every b, it's saying that that's equivalent. It's the equivalence theorem. The equivalence theorem is a lot of different statements that are all equivalent, have the same truth value. And it tells you that two of them are equivalent. It says ax equals b is consistent for every b is equivalent. Has the same truth value as the statement the determinant of a does not equal 0. Okay? And so, if b, this little b here, is the vector v1, v2, v3, and the x here is actually the c values. Those are the unknowns. X is the unknown, and so here the unknowns are the c values. Then, what we're saying is that this linear system, using where A is the coefficient matrix, corresponding group, ax equals b is consistent for every b. That's equivalent to saying the determinant of the cofactor matrix is non-zero. Of the coefficient matrix is non-zero. Okay? By the equivalence theorem. And so what we have to do is take the determinant of the corresponding coefficient matrix. And if that determinant is non-zero, then we know that this has a solution for any v we choose in R3, or any values for v1, v2, and v3 we put there. And so the determinant of A here is equal to the determinant of the coefficient matrix there. So I'm going to take the cofactor expansion along the third row, and it's going to be the determinant of this guy plus 4 times the determinant of that guy, right? So you're just finding the determinant, and then this times this minus that times that is 6 minus 27, which is negative 21, plus 4 times 9 minus 4, which is 5. And so this is negative 21 plus 20, which is negative 1, which is not equal to 0. It's close to 0, but not 0. So the determinant of this is non-zero. That's true. And so it's also true, because they have the same truth value, that ax equals b is consistent for every b. That means for any vector v you choose in R3, where v1, v2, and v3 are its components, this linear system has at least one solution. That means there are values for c1, c2, and c3 that satisfy all three equations, or such that c1, v1 plus c2, v2 plus c3, v3 is equal to your vector v, which is v1, comma v2, comma v3. Okay? So the determinant of the coefficient matrix is non-zero, and by the equivalence theorem, that's equivalent to saying that you can plug in any values for those three constants, and that linear system has at least one solution. Which means that that equation has at least one solution. Okay, the solutions are assignments for all the C's there. Okay, so we showed that set S spans R3 now. Okay, because every vector V in R3 can be written as a linear combination of the vectors in set S, V1, V2, and V3. So every vector in R3 can be written as a linear combination of V1, V2, and V3. That's why the set S formed by those three vectors spans R3. Okay, so linearly independent spans, that means it's a basis. And so set S is a basis for R3. Those three vectors form a basis for R3. Okay? That's example 3. So example 4. So these 4 vectors will form basis for M sub 2, 2. This is the standard basis for M sub 2, 2. Okay, so these 4 matrices are vectors in the vector space M sub 2, 2, right? So M sub 2, 2 is the vector space of 2 by 2 real matrices, where the entries are real numbers, right? So M sub 2, 2 is a vector space of 2 by 2 real matrices, right? Vectors are not just the vectors you learn about in physics. Vectors are just elements of what we call a vector space, the set, as part of our definition of vector space. That's what a vector is now. In a more abstract sense, a vector is just an element in the set capital V, which is part of your vector space, right? And so M sub 2, 2, comma, the standard addition on matrices and the standard scalar multiplication on matrices, these 3 things, the team of those 3 things is what a vector space is. And the elements of M sub 2, 2, any 2 by 2 matrix with real entries, is a vector of this vector space. Okay? And so those 4 2 by 2 matrices, they're elements of M sub 2, 2, but they also form a basis for M sub 2, 2. So M sub 1, M sub 2, M sub 3, M sub 4 form what's called the standard basis for M sub 2, 2. It's a basis for M sub 2, 2 that's called the standard one because it's the one you usually think of for this vector space, okay? And so these 4 vectors are linearly independent and they span all of M sub 2, 2. Okay? If you take any vector M in M sub 2, 2, you can think of it as a linear combination of M1, M2, M3, and M4. Okay? So if you take any vector M in M sub 2, 2, it can be written as a linear combination of those 4 matrices, and so that means that you have spanning. Okay, so the set S, those 4 vectors span M, and then also they're linearly independent, because if you take the equation C1 M1 plus C2 M2 plus C3 M3 plus C4 M4 is equal to 0. The only solutions are when all the C values are 0. Okay, so this equation holds if and only if C1 equals C2 equals C3 equals C4 equals 0. Okay, and so that means that the set is linearly independent. The set containing those 4 vectors, M1 and M4. So since you have spanning and you have linear independence, those 4 form a basis called the standard basis for M sub 2, 2. Okay, so that's example 4. Okay, next. Okay. So the empty set is the basis for the zero vector space by definition. Okay, so by definition, we're saying the empty set is the basis for the zero vector space. Okay, we showed earlier in another video that the zero vector space is indeed a vector space. Okay, that satisfies all 10 axioms for a vector space. And so we already saw how this is a vector space. And so it has a basis, and we're going to call the empty set its basis by definition. Okay? So no proof needed there because it's by definition. Okay. Okay, and then I'm going to put a table up here. And these are finite dimensional spaces, and these are infinite dimensional spaces. Okay, so the first finite dimensional space is R to the n. The second one is P sub n, and the third one is capital M sub n. Okay, so the finite dimensional vector spaces are R to the n, P sub n, and M sub mn. Okay, these are the polynomials of degree at most n. This is the vector space of matrices with m rows and n columns. Okay, and this is with standard addition multiplication on matrices, the standard addition multiplication on polynomials, and the standard addition and scalar multiplication of vectors in Rn. Okay, standard addition and scalar multiplication for corresponding each of these three. Okay, and then the infinite dimensional spaces, one are P sub infinity, which is this is just all polynomials. Okay, it's a vector space of all polynomials of any order. That's P sub infinity. It's infinite dimensional. That means there is not a set of finite vectors which forms a basis for that vector space. 2, R infinity. Okay, so now these are vectors with infinitely many components. So this does not include vectors with finitely many components. I mean, they're only vectors with infinitely many components. And it's infinite dimensional because there is no basis for this space, vector space, consisting of only finitely many vectors. Okay, 3, capital F of negative infinity comma infinity. And so these are the set of functions defined on the real line. Okay, 4, C negative infinity comma infinity. This is the vector space of continuous functions defined on the real line. 5, Cm. These is the vector space of functions defined on the real line that are m times continuously differentiable. Okay, this is the vector space of functions defined on the entire real line that are m times continuously differentiable. That means it has continuous derivatives of order 0 up to including m. The 6th infinite dimensional vector space is C infinity of negative infinity comma infinity. This is the vector space of functions defined on the entire real line that are continuous derivatives of all orders. That means you can take the derivative as many times as you want, and every time you do, no matter how many times you do it, you're going to get a continuous function. So you could take the 50th derivative of your function, and you'll get something that's continuous. You could take the millionth derivative, and you'll get something that's continuous, and then you can keep taking derivatives as many times as you want. Okay? And so that's a vector space also. And so all 6 of these are infinite dimensional vector spaces. There is no finite basis for any of these 6 vector spaces. Okay? This vector space has exactly n basis vectors. The basis for this vector space has exactly n plus 1 vectors, and the basis for this vector space is m times n vectors. And so all 3 of them are finite. N is finite, n plus 1 is finite, and m times n is finite. Okay? All these infinite. Okay. Let's keep going. So if you encounter any of these 9 spaces from this table, you can know whether or not it's finite or an infinite dimensional vector space. Okay, so theorem 4.1. 4.4.1. If capital S is the set V1, V2, up to including Vn, it is a basis for a vector space capital V, then every vector little v in capital V can be expressed in the form V equals C1 V1 plus C2 V2 plus dot 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 plus Cn Vn in exactly one way. Okay, so this is theorem 4.4.1. Okay, so if that set S is a basis for V, then every vector little v in capital V can be expressed in that form in exactly one way. Okay, and so it's very, it's actually a very useful thing to have happen, that you can only express V in exactly one way as a linear combination of those vectors, right? So having a basis for vector space is very useful. Okay? And definition 2. If this set S, the same set over there, is a basis for a vector space capital V, and V equals C1 V1 plus dot 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 plus Cn Vn is the expression for V in terms of the basis capital S, then the scalars C1 up to including C sub n are the coordinates of V relative to S, relative to the basis S. S vectors in case. Okay, the vector C1, C2, up to including Cn is called the coordinate vector of V relative to S. Excuse me, sorry. And the abbreviation is V in parentheses with the subscript capital S. Okay? So this notation is a notation for the coordinates of V relative to S. You would say this is equal to that. Okay? And so this is definition 2. This is the definition of the coordinates of a vector relative to a basis S. Okay? These are the scalars. These are the coordinates of your vector relative to a basis S. What you need is a representation of your vector in that way. And then the coefficients of each of these vectors correspondingly are the components of the coordinates of V relative to S. Okay? Okay. So just as my own example, let's say you took as a basis set 1, 0, 0, 1, right? This is the standard basis for R2. Then if you took the vector V, which is 5, 4, right? Vector 5, 4, this would equal 5 times vector 1 comma 0 plus 4 times vector 0 comma 1. So if I pull this vector v1 and this vector v2, this would be 5v1 plus 4v2. But the coordinates of v relative to s would be 5 comma 4. It would actually be the same vector as the original vector. But it would be because I express v as equal to 5v1 plus 4v2. And so the coefficient next to v1 is the first component, and the coefficient next to v2 is the second component. Okay? So the book does this implicitly without adding notation. What they do is this basis s, they consider it what's called an ordered basis. They apply order to the vectors in the basis. It's not written there, and there's technically a notation for doing that. And so the book skips that and doesn't worry about it when talking about it. Technically, there's an order to these basis vectors. And so this is the first basis vector, and that's the second basis vector. Okay, so normally in a set, the order doesn't matter. But here now, we're saying that this is the first one, that's the second one. And that's not written in the notation. It's just a lazy, maybe an easier way to be introduced to it without worrying about how to define an ordered basis. Okay, so this is the first basis vector, and that's the second basis vector. And so the vector v 5 comma 4 is 5 times the first basis vector plus 4 times the second basis vector. And so the coordinates of v relative to that basis is 5 comma 4. Okay? You just need to express your vector v as a linear combination of the basis vectors. And then, from the order that you assign to your basis vectors, the coefficients of those vectors in the linear combination are the corresponding components of the coordinates of that vector relative to your basis. Okay? Okay. Okay, 5 and 4. Okay. Okay. And so now if you look at the vector space V, and you look at the vector space Rn, there's a one-to-one correspondence between the vectors in V and the vectors in Rn. Okay, so there's a one-to-one correspondence between these two spaces. And this is figure 4.4.6 in the book. Okay, so figure 4.4.6 in the book shows how there's a one-to-one correspondence between a vector space V and R to the n for some n. And what that means is that with this correspondence in mind, for some n, you can associate every vector in your vector space with exactly one n tuple in Rn. Okay? And so the coordinates of a vector relative to a basis is a way of simplifying a vector space. Instead of having your original vector space, which may not be in Rn, maybe it's a vector space of matrices, maybe it's a vector space of polynomials, you can associate all of your vectors in your vector space, which might be a little bit more difficult of an object. You can associate all of those objects with now an n tuple in Rn, which what you might normally think of as a vector. And so this one-to-one correspondence means that in a one-to-one way, you can associate all the things here with exactly one n tuple there. And that n tuple is the coordinates of v relative to s that I defined in the last board, on the other boards previously. Okay? So when you find the coordinates of a vector relative to a basis for your vector space, you're finding with that definition in mind, you're finding the correspondence between all the vectors in the vector space and n tuples in Rn. Okay? Okay? So in example 7, if in the special case your vector space is Rn and S is the standard basis, and the standard basis is E1 to En. So if you have V is n space, your vector space is n space with the standard basis, then things are really convenient because the vector you're talking about is equal to its coordinates relative to S. And so in the first example I showed you, that's what happened, right? So if you have a vector space which is Rn, and if you have the standard basis S for that Rn, then the coordinates for any vector V, its coordinates relative to S is itself. Okay? Okay. So for instance, if you have a vector V which is A, B, C, which is a vector in R3, because there's 3 components, and you have the standard basis S for it, right? S here, the standard basis is E1, comma E2, comma E3. Then that vector V, the coordinates of that vector relative to S is exactly the same as the vector V. Okay, and why is that? And that's because the vector V, which is ABC, is equal to A times E1 plus B times E2 plus C times E3. So now you can express V as equaling to A E1 plus B E2 plus C E3. And so the coordinates of V relative to this basis S is, well, since E1 is the first one, E2 is the second, and E3 is the third, the coefficient of the first basis vector is the first component of the coordinates. The coefficient of the second basis vector is the second component of its coordinates. And the coefficient of the third basis vector is the component of the third. Is the third component of its coordinates relative to S. Right? And the order is implicitly described by the order you put it in the set. Even though the notation for an ordered basis is not put there, it's assumed that this is an ordered basis. But this is the first basis vector, that's the second, and that's the third. Okay? So V is equal to A E1 plus B E2 plus C E3 means that the coordinates of V relative to the standard basis S is A comma B comma C. Okay. Okay, so now, okay, so example 9 in this section, for part A, you want to find the coordinate vector of V, which is equal to 5 comma negative 1 comma 9 relative to the basis relative to the basis capital S, which is V1, comma V2, comma V3, in example 3. So find the coordinate vector of that V relative to that basis. Okay, so this V, which is 5 comma negative 1 comma 9, is equal to C1 times V1. Okay, so let me just C1 times V1, which is 1 comma 2 comma 1, plus C2 times V2, which is 2 comma 9 comma 0, plus C3 times V3, which is 3 comma 3 comma 4. Okay, so I just want to find the coordinate vector of V relative to that basis. I want to find C1, C2, and C3 such that that equation holds. And then the coordinates of V relative to that basis S is going to be C1, comma C2, comma C3. Okay, so once I find the coefficients here, that will be the first, second, third components of the coordinates of that vector V relative to that basis S. Okay, and so now 5 comma negative 1 comma 9 is equal to C1 plus 2C2 plus 3C3 comma 2C1 plus 9C2 plus 3C3 comma C1 plus 4C3. Okay? Okay, and so correspondingly, you get a linear system. C1 plus 2C2 plus 3C3 is equal to 5. Okay, so I'm just going to write out this out here. C1 plus 4C3 is equal to 9. So here's your linear system. Okay, And so you just want to find solutions for C1, C2, and C3 for all the equations that linear system. And that's the values you can plug in here where that equation holds. And that will be the coordinates of V relative to S. Okay, there should be exactly one solution because we know that the coordinates of V relative to S has a one-to-one correspondence with the vector space, right? We can only have one solution there. Okay. So now you have your linear system here. Okay, so that's your linear system. And when you solve this system, you can get this to reduced echelon form, and you will get this. Okay, and so getting this matrix to reduced echelon form, you get that, and that implies that C1 is equal to 1, C2 is equal to -1, and C3 is equal to 2. Okay, and so the coordinates of V relative to S, which is that, you plug in the values of C there, you get 1, -1, 2. So the coordinates of V relative to S is that. And that's the answer to this part A, example 9. Okay, and then for part B, what we want to do is find the V in R3, find vector V in R3 such that the coordinates of V relative to the space S is equal to -1, 3, 2. Okay, well that's easy actually. So V is equal to C1 V1 plus C2 V2 plus C3 V3. This is equal to this is C1, C2, C3. So C1 is -1, C2 is 3, and C3 is 2. So C1 is -1, C2 is 3, and C3 is 2. So, and V1 was this, V2 was that, and V3 was that. So you get -1, 2, 1 plus 3 times plus 2 times that. Okay, so I'm just plugging in what V1, V2, and V3 are. And because I have the coordinates of V relative S, I know what C1 is, C2 is, and C3 is. And I just plug all 6 of those things in, and I can find V. And so now this is equal to -1, 5. This is 11, 31, 7. Okay, so you just negative that vector plus 3 times that vector plus 2 times that vector. You get V is equal to 11, 31, 7. And so that's the vector V with those coordinates relative to that basis S. Okay, so that's example 9, part A and B. Okay. Okay, so that's the end of 4.4. And so now it's 4.5. Okay. So 4.5 is on dimension. Okay, so theorem 4.5.1. All bases for a finite dimensional vector space have the same number of vectors. Okay, so all bases for a finite dimensional vector space have the same number of vectors. So even though you can have more than one basis for a vector space, in fact you have infinitely many vectors, infinitely many bases for the same vector space, they all have to have the same number of vectors in them. Okay? That's theorem 4.5.1. Theorem 4.5.2. let capital V be n-dimensional as a vector space, and V1 to Vn is a basis for that vector space. Okay? Any basis. Part A, if a set in capital V has more than n vectors, then is linearly dependent. Okay, and part B, if a set in V has fewer than vectors, then it does not span V. Right? So in order to have a basis, you need linearly independence and spanning. But it's very easy to have a set that's not linearly independent or is dependent, or have a set that does not span all of V. And it's very easy to have that happen. And so there's some things that can happen where right away you know it's linearly dependent or it doesn't span your vector space. So if V is n-dimensional, and you have n vectors forming a basis for that n-dimensional vector space, then if a set in V has more than n vectors in it, it's linearly dependent. And if a set in V has fewer than n vectors, then it does not span V. Okay? So an n-dimensional vector space has exactly n vectors in its basis. But if you have a set with more than n vectors in it, it's linearly dependent. And if you have a set with fewer than n vectors, it does not span V. Okay, so it's written there in the box. That's Theorem 4.5.2. Okay, and this is Theorem 4.5.1. Okay, so you have to read all this and each individual thing and think about each individual idea for a little while. Okay. Next. Definition 1, the dimension of a finite dimensional vector space So we talked about a finite and infinite dimensional vector space without saying exactly what the dimension was, right? Okay, so the dimension of a finite dimensional vector space, capital V, is denoted by dim of V, dim in parentheses V, and is defined, it's denoted that way, and is defined to be the number of vectors in a basis for V. The zero vector space has dimension 0. Okay, this is definition 1. Okay, so definition 1 is the dimension of a finite dimensional, definition 1 for 4.5. The dimension of a finite dimensional vector space V is defined by dim of V and is defined to be the number of vectors in a basis for V. The zero vector space has dimension 0. So every basis for a vector space has the same number of vectors. And so since every basis has the same number of vectors in it, we can define the dimension of the vector space to be the number of vectors in any basis. Because once we know the number of vectors in any basis, we know the number of vectors in every basis. And that number is the dimension for a vector space. Okay? So the dimension of R to the n is n, okay? And so that means that any basis for R to the n has exactly n vectors in it. You can find a basis for R to the n that has n basis vectors. And one such basis is the S, which is E1, E2, up to including E sub n that we talked about before. That has exactly n vectors in its basis. And so we found a basis with n vectors in it, and so the dimension of R to the n is n. Okay? Also, the dimension of P sub n, I mentioned, is n plus 1. And so the reason for that is that even though there's an n here, right, and you might think there has to be n, the answer has to be n because I put an n there. S is a basis for S is 1x x squared, x cubed, up to including x to the n. Right? So a basis for P sub n is not just x to x to the n, it would be 1 also, because you have a constant term at the beginning of the polynomial. You have a naught plus a1x plus a2x squared plus a3x cubed plus dot 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 plus a sub n x to the n. The coefficients a1 to an, right? I mean, you have the vectors x to the n, but you also have the 1 in the beginning. There's a 1 vector there also, the constant vector. So P sub n needs an additional 1 more than you would think. It doesn't, you can't just have x from x to the n, you have to have the 1 vector there also. Or you need another vector there. And so this would be the standard basis for P sub n. Other bases, you wouldn't need a constant vector there, but you would still need n plus 1 vectors, but they would just be in such a way where that would be taken care of. It'd be a little complicated, right? Okay, at this point. Okay, so the dimension of P sub n is n plus 1. And the dimension of m sub m n is equal to m times n. So the dimension of the vector space of m by n matrices is m times n. And that's because m sub m n is the vector space of matrices with m rows and n columns. And so the basis would be made up of matrices that has a 1 in one position and zeros everywhere else. And so each basis vector for m sub mn would have a 1 in one entry and zeros everywhere else. And there's m rows and n columns. There's m times n entries. And so each basis vector would correspond with having a 1 in one of those m times n positions and zeros everywhere else. There would be m times n basis vectors for a basis for m sub mn. And so this dimension is m times n. Okay? So those are 3 examples of the dimensions of vector spaces. Okay, example 2. If S is equal to the set V1, V2 up to including V sub R is linearly independent. It's a linearly independent set. That's what I mean by saying it is linearly independent. Then the dimension of the span of S is equal to R. Okay? So, what does this mean? Okay, so if you have set S, which is vectors V1 to VR, and it's linearly independent, right? So you have to make sure you know what linear independence means. If you have the set S that's linearly independent, then the dimension of this vector space is R. The span of a set is a vector space. So given any set S, its span is a vector space, okay? Well, we take S to be a set of vectors in a vector space, right? So then the span of that S is a vector space. And so taking this set S, which contains vectors V1 to VR, the span of it is a vector space and it has a dimension. And the dimension of it is R, if these R vectors are linearly independent. So if you take R linearly independent vectors, they form a set S whose span, the dimension of that span is R. Okay? Example 3 says x1 plus 3x2 minus 2x3 plus 2x5 is equal to 0. 2x1 plus 6x2 minus 5x3 minus 2x4 plus 4x5 is equal to 0. 5x3 plus 10x4 that's equal to 0 there. This is minus 3x sub 6 is equal to 0. Plus 15x sub 6 is equal to 0. And then this is 2x1 plus 6x2 plus 8x4 plus 4x5 plus 18x sub 6 is equal to 0. Okay, so you have this linear system, and if you write it, if you find its corresponding augmented matrix, get it to reduced echelon form, find the general solution of this linear system. That way, you get the solution space is, so right, you find the parametric equations, and you get your parametric equations for x1 is equal to negative 3r minus 4s minus 2t, x2 is equal to r, x3 is equal to negative 2s, x of 4 is equal to s, x of 5 is equal to t, and x of 6 is equal to 0. Okay, that would be the general solution for this linear system represented in parametric equations, right? So that would be that would be the solution space. And then if we wrote that solution space as the coordinates x1, comma x2, comma x3, comma x4, comma x5, comma x sub 6, that would equal to r times, so we would plug in x1 through x6 here, and then we would separate all the letters, and we would get r times negative 3, comma 1, comma 0, comma 0, comma 0, comma 0, plus s, negative 4, comma 0, comma negative 2, comma 1, comma 0, comma 0, plus t times negative 2, comma 0, comma 0, comma 1, comma 0. So then thus this is equal to r times this plus s times this plus t times that. And so I've now expressed the solution space as being r times this vector plus s times this plus t times that. If I call this vector v1, and I call this vector v2, and I called this vector v3, then those three vectors would span the solution space, because I could take any solution x1 to x6 here, and I could write it as a linear combination of v1 to v3. So these three vectors would span the solution space, and you could see that you could show that these three vectors are linearly independent. And so therefore, v1, v2, v3 here form a basis for the solution space of that linear system. So this linear system has a solution space. It's a set of solutions, and it's a vector space. We found a basis for it, and it's these three vectors. And so these three vectors span your solution space. You could take any solution and represent as a linear combination of those three vectors, and these three vectors are linearly independent. And so those three vectors form a basis for a solution space, and so we have a vector space, the solution space, which has a basis with exactly three vectors in it. And so that means this solution space has dimension 3. Okay, so that's how this fits into this section on dimension. We found the solution space, we found a basis for the solution space, which has exactly 3 vectors in it. And that means that our solution space here is a vector space of dimension 3. Okay? Okay, so that's example 3. Okay, so now, so now let's do another theorem. So this is theorem 4.5.3. And this is the plus minus theorem. And so even though it's called the plus minus theorem, it's difficult. Okay, so plus minus theorem is let capital S be a non-empty set of vectors. In a vector space capital V. Okay, so S is a non-empty set of vectors in capital V. Part A, if S, that set S is linearly independent. Capital S is linearly independent, and if V is in, and if little v is a vector in capital V, I'm using notation that a lowercase letter is a vector in the set, and capital V is the vector space itself. So, and if little v is in capital V, lying outside the span of S, then the set S union the set containing V is still linearly independent. Okay, so it's called, this is the plus part of the theorem because we're taking a set S and we're adding to it the vector V by considering the set S union the set containing V. By taking the union of S and the set containing only V, we're now adding the vector V in the set we originally had S. So now the new set is the original set S along with the vector V put in it. So we added that into the set. Okay, and that set is now still linearly independent. Okay, so let's say, for instance, we're looking at R3. Draw a picture of this. So here's the x-axis, y-axis, and z-axis. And now if capital S is linearly independent, so if you take this vector here, and this vector here, okay, so let's say we take, we took this vector v1 here and this vector v2 here. Then the span of v1 and v2 is non-collinear vectors in R3. The plane, there would be a plane determined by those two vectors v1 and v2. And so the plane is the plane that those two vectors sit on. Now the span of the set containing v1 and v2 is the entire plane they sit on. That's the span of v1 and v2. If I take a vector v that's in my vector space here, this is an example illustrating it. If my vector space is R3 in this example, and the span of v1, v2 is here, and if I take a little v that's not on the plane, this little v is not on that plane, then if I were to take the vector v that doesn't lie in that plane, and if I were to add it to the set v1, v2, that set would be linearly independent. That's what part A of this theorem says. So v1 and v2 being non-collinear in this example as vectors in R3, v1 and v2 would determine a plane, the plane that those two the only plane that those two non-collinear vectors could sit on. And so that plane, if you take a vector that's not in that plane, then if you take the set v1, v2, and then you include in that set the vector v that does not lie in that plane, this set is also linearly independent. Remember, we started with v1 and v2 were linearly independent. Okay? The original set S, which is v1, v2, was assumed to be, this is assumed to be linearly independent. But if we were to just put the vector v in there, we would not know whether or not that set would be linearly independent. But by this theorem, if the assumptions of this theorem hold, then the conclusion says you can add that vector v to that set, and it's still linearly independent. The new set here with V in it is also linearly independent. That's the conclusion of part A of this theorem. You can add vectors V that satisfy the conditions of this theorem into your set, and you still have a linearly independent set. Okay? So again, this plane that V1 and V2 sit on, that's the span of the set S. And then the vector V here is that's not on that plane. That's a vector V outside the span of V of set S. And so I can then add V into the set S, and I still have a linearly independent set as a conclusion. Okay? Part B. If little v is a vector in set S that is expressible as a linear combination of the other vectors in S, and if S minus the set containing V so then let's define it. Then that set and S span the same space. Or another way to put it, the span of S is equal to the span of S minus the set containing V. That's part B of the theorem. Just the minus part. So if little v is in capital S, is expressible as a linear combination of the other vectors in S, then the set S with the vector v removed and the set S span the same space, or this equation. The span of S is equal to the span of the set S minus the set containing V. Okay? Now when you take a set and you subtract another set, you remove the elements in this set from that set. So an example of set subtraction would be if you take the set 1, 2, 3 and you subtract the set 5, 3, you would take the set 1, 2, 3 and you remove from it 5 and 3. But since 5 is not in that set, it doesn't change it, but 3 is, and so you remove 3. And you get 1, 2. Okay? So this set minus that set means that you take this set and you remove from it any of the elements in this set that are in that set. And so here you can't remove 5 from there because there is no 5. But you can remove a 3, and so you remove the 3, and you get 1, 2. Okay? So the set S minus the set containing V is taking the set S, and then if V is in that set, you remove it from it. And if V is not in that set, it stays the same. Okay? That's the set S minus the set containing V. Okay, so the conclusion says that the span of S and S minus the set containing V are the same. Okay? That means that V doesn't change the span of your set. That vector V doesn't change the span of the set. Okay, and so you can remove it and the span doesn't change. Okay, so if little v is in the set, so that happens if the assumption holds that if V is in the set, vector V is in set S, is expressible as a linear combination of the other vectors in S, then that happens. Okay, so if you can express the vector V as a linear combination of the other vectors in S, then you don't need the vector V for the span of S. And so the span of S equals the span of S minus the set containing V. Okay? And so that's part A and B of the plus minus theorem, theorem 4.5.3. Okay? And so this is part 1 of this lesson. And so this is extended lesson. And so the next video I'm posting will be part 2 of the same lesson. Okay? So I'll see you there.